Why is the universe expanding? Chapter 1. The Breath of Space. You are alive inside a story that keeps getting bigger. At first, that sentence sounds like poetry, the sort of line a starry-eyed narrator might murmur over slow footage of galaxies. But it is also a literal description of your current address. You inhabit a universe whose very fabric, space itself, is stretching, like a slow inhale that never quite becomes an exhale. The cosmos is expanding. Galaxies are not flying apart through empty space as bullets through air. Rather, the space between them is growing, gently carrying them along. Even as you read, the distances that define reality between clusters of galaxies, between the cosmic landmarks we use to draw our maps, are being redrawn. Why is the universe expanding? To answer that, we must first accept a simple, counterintuitive premise. Empty space is not nothing. Nothing is a slippery idea. You can empty a room of furniture, a jar of air, a thought of its words, but the void that remains, whatever we imagine when we say nothing, is rarely empty at all. In physics, space is a kind of something. It has geometry. It curves in response to mass and energy. It can ripple, as in gravitational waves. And, crucially, its size can change. The universe expands because space is dynamical. It obeys rules. Those rules are written in a language we discovered barely a century ago, when a patent clerk imagined riding on a beam of light and followed that thought to its logical end. Einstein's general theory of relativity says gravity is geometry. Matter and energy tell spacetime how to curve. Curved spacetime tells matter how to move. If you have ever watched a marble roll along a dented sheet, spiraling toward a heavy bowling ball in the center, you have tasted the metaphor. Mass creates dents, curvature, and those dents guide motion. Now extend that idea to something larger, the fabric of the cosmos. Ask, if the universe contains matter, light, and whatever else might haunt the vacuum, what shape must space and time take on the largest scales? Einstein's equations allow many possibilities: static, glowing, collapsing, rebounding, expanding universes. The equations themselves do not demand an expansion. They permit it. But when you pour the actual stuff of our universe into those equations, the galaxies, the cosmic radiation, the faint pressure of the vacuum, they predict a particular behavior. The simplest, most natural, and most stable way to balance the books is a universe that expands. You don't have to take this on faith. We can watch the expansion. In the early 20th century, astronomers looked at the light from distant galaxies and noticed an odd thing. The light was stretched, reddened, as if the galaxies were receding. That reddening is not the Doppler effect of ordinary motion alone. It's the signature of space itself, stretching the waves of light as they traverse the abyss. Imagine painting stripes on a rubber band, then pulling the ends apart. The stripes themselves widen. Light from distant galaxies carries the history of the band stretching. This is the Hubble-Lemaître law in action. The farther a galaxy is, the faster it appears to recede, not because it is rocketing through space at unimaginable speed, but because there is more space in between to expand. So the universe is expanding. But the question remains, why? Let us walk carefully. There are at least 3 layers to the answer. First, there is the how, the mathematical law that governs expansion. Second, there is the what, the ingredients matter, radiation, dark energy, whose combined effect sets the pace. Third, there is the why this way, the deeper origin story that tells us why these ingredients exist and why their strengths are what they are. Begin with the how. In cosmology, we quantify expansion with a scale factor, a single function of time, Alra in Krug, that tells us how distances grow. If a galaxy is 10 million light-years away, when the scale factor is Brand 1, A equals 1. Then, at a later time when ent 2, A equals 2, that galaxy is 20 million light-years away, neglecting local tug-of-war between galaxies in small groups. The rate at which ISNO and 8 changes is captured by the Hubble parameter IM, wood was amber, and 8. HT equals A. Einstein's equations, applied to a universe that is on average the same in every direction, homogeneous and isotropic, reduced to the Friedmann equations, which are the heartbeat of cosmology. They relate X, its duty, 8, to the energy content of the universe, the density of matter and radiation, the curvature of space, and any constant energy density of the vacuum. In a slogan, the expansion rate is determined by what the universe is made of. Now the what. Our cosmic inventory is odd. Ordinary matter, the atoms in stars and people, makes up only a minor fraction. Dark matter, an invisible mass that tugs on galaxies without shining, adds a bigger chunk. Radiation light, neutrinos, contributes a whisper today, though it ruled the early universe. And then there is dark energy, the strangest contributor of all, a smooth energy inherent to space itself with negative pressure that accelerates the expansion. When the universe was young and dense, matter and radiation dominated. Their gravity slowed expansion, like brakes on a downhill car. But as the universe spread out, matter thinned, radiation thinned faster, and the constant energy of the vacuum began to matter more. Curiously, the pressure associated with this vacuum energy leads not to attraction, but to repulsion on cosmic scales. Instead of applying the brakes, dark energy presses the accelerator. The measured expansion of our universe is not just continuing, it is speeding up. This is not a flourish added to make the tale exciting. It's measured in the ways astronomers measure anything, by cross-checking methods that have no reason to agree except that they track the same reality. We watch distant supernovae, the standardizable candles whose inherent brightness we can calibrate, appear dimmer than they would in a decelerating universe. We map the pattern of galaxies across billions of light years and hear the fossilized sound waves from the early universe in the arrangement of those galaxies today. We read the fine modeling of the cosmic microwave background, the afterglow of the hot young universe, and find that an accelerated expansion best fits its subtle fingerprints. Like three witnesses describing the same suspect from three different streets, these measurements point to the same culprit, dark energy or something very much like it. But naming is not explaining. Calling it dark energy means we don't fully know what it is. One candidate is the cosmological constant L, which Einstein once introduced as a mathematical knob to tune a static universe, a choice he later called a blunder, for reasons of history more than mathematics. As a physical entity, L is simple. It's an energy density that belongs to space itself, unchanging in time, the same everywhere. Empty space is not empty. It seethes with quantum fields, and even the lowest energy state of those fields may contribute a finite energy per cubic meter. Put such a constant into the equations, and the result is an accelerated expansion, the very one we infer. The problem is that theoretical estimates of vacuum energy tend to be absurdly larger than what we observe by factors that beggar the imagination. Why is the actual value so small, yet non-zero? Why now? These are live, sharp questions, and honest answers begin with humility. We don't know. The cosmological constant could be a clue to new physics, a hint that our intuitions about vacuum, symmetry, and gravity are incomplete. Another possibility is that what we call dark energy is not energy at all, but a misunderstanding of gravity on the largest scales. Perhaps general relativity, a theory tested exquisitely in solar systems and black hole binaries, needs a gentle modification across billions of light years. There are proposed theories, elegant, complicated, sometimes fragile, that change how space-time curves in the emptiest places, mimicking a cosmic repulsion. These are fascinating, and they are carefully checked against observations, which so far continue to favor the simplest interpretation: a cosmological constant or a near-constant dark energy. Still, the door remains open, and we keep testing. We might be tempted to ask for a more satisfying why. Why should space be dynamical? Why should there be any vacuum energy at all? Why should quantum fields imbue emptiness with pressure? Here the answers become less like engineering and more like archaeology, a dig through layers of cause until we hit bedrock. The deep why of expansion may lie in the initial conditions of the universe. If the universe began in a hot, dense state, as all the evidence suggests, and if its early moments included an episode called inflation, a burst of exponential expansion driven by a different kind of vacuum energy, then the seeds of today's expansion were planted early. Inflation would have stretched the universe smooth and flat on large scales, leaving it poised to continue expanding under the gentler influence of matter, radiation, and later dark energy. In this view, expansion is the default state of a universe born with positive energy density and the right pressure conditions. You could say the universe expands because it cannot help it. Its equations, given its contents, demand it. But even that story raises further whys. Why did inflation start? Why did it end where it did, leaving just enough irregularity to make galaxies, yet not so much as to smash them apart? Why does the vacuum energy today have the peculiar smallness it does? You feel the tug of metaphysics at the edge of physics, the way a climber feels empty air beyond the cliff's lip. Some physicists imagine a multiverse, a collection of regions with varying laws, where ours is simply one that allows structures and observers, and the smallness of the cosmological constant is an anthropic selection. If it were much larger, galaxies would not form, and we would not be here to wonder. Others resist this and search for a symmetry or mechanism that sets the constant to its measured value. The jury is still out. The question remains a living frontier. If this sounds unsatisfying, we don't know. Take comfort in how far the known reaches. We can write the history of expansion like a diary. In its first instance, the universe may have inflated, its size doubling again and again in a sliver of a second, flattening and smoothing the cosmic canvas. A hot plasma followed, thick with light and particles. As expansion continued, the plasma cooled. Protons and electrons married into neutral atoms. Light decoupled and began its long journey across space. The cosmic microwave background carries that memory. Once gravity could act unimpeded by radiation, the small ripples in density began to grow, forming webs of dark matter that lured gas and later stars. Galaxies bloomed. During this long, middle-aged, decelerating era, matter ran the show. Then, a few billion years ago, recent in cosmic terms, the balance tilted. Dark energy rose to prominence, easing the brakes and then pressing the pedal. The expansion, once slowing, began to accelerate, not with violence, but with inexorable grace. The consequences are profound. In an accelerating universe, there exist horizons not unlike the one created by a black hole. Beyond a certain distance, light emitted today will never reach us. The space between expands too quickly. The observable universe does not shrink, but our causal neighborhood becomes more isolated. Over stupendous spans of time, galaxies not gravitationally bound to us will fade into invisibility. The night sky will grow empty. The cosmic web will thin. This is not cause for despair. It is reason to savor the present, an era in which the universe is both knowable and rich with signals from its past. We live in a sweet spot, able to trace the expansion's history across scales, to measure its ingredients, to ask why with data in hand. Let us return to the first sentence and deepen it. You are alive inside a story that keeps getting bigger. And the reason it does is that the universe is a dynamical solution to its own laws. Given the energy it contains, the density of matter, radiation, and the vacuum, the geometry that fits is one whose scale factor grows. Expansion is not an external push. No one is blowing into the balloon. The balloon is the way it evolves when the air inside has the pressure it has. You could strip away stars and still the rubber would stretch, because the vacuum itself has breath. Skeptics sometimes ask, if everything is getting bigger, why aren't we? If space is expanding, why does a ruler not expand with it? Why does a galaxy hold together? Why does a solar system not drift apart? The answer is that expansion is a large-scale phenomenon. Local structures bound by gravity or by other forces do not partake. The same equations that tell space to expand on average also tell galaxies to remain intact where their internal gravity is strong. The rubber band is being stretched, yes, but the knots tied in it, the galaxies, stars, atoms, stay knotted. Expansion is the change in the average distance between the knots. There is another way to picture it. Imagine a loaf of raisin bread rising in an oven. As the dough expands, the raisins move away from one another. None of the raisins is the special center. Each sees the others recede. The loaf does not expand because raisins propel themselves through the dough. Rather, the dough itself stretches. Now, clench 2 raisins together with a toothpick. That cluster will not expand with the dough. Its bond is stronger than the gentle push of the rising loaf. Our galaxy is such a clump. The Milky Way, Andromeda, and our small group are tied by gravity. Across the larger loaf, though, expansion rules. This humble kitchen image is not perfect. Real space is not embedded in air, and there is no oven, but it suggests the right kind of thinking. The universe expands because its dough does. Its dough is spacetime. An audiobook must not only inform, it must breathe. So inhale with the universe. Picture the first photons loosed into the newly transparent cosmos, gliding outward as ocean swells on a calm day. Picture the first stars kindling in dark halos, their light striding into an expanding sea. Picture the faint pressure of the vacuum so small that it hides behind every stronger effect for billions of years, gradually assuming the throne and guiding the cosmic rhythm onward. Why is the universe expanding? Because the relationship between energy and geometry, written by general relativity and filled by our cosmic ingredients, prefers this dance. Because vacuum energy, whether as a true cosmological constant or something we have yet to name, lends space-time a gentle push that over cosmic time becomes a shove. Because initial conditions born from a hot beginning, perhaps gilded by inflation, set us on a path where expansion was the natural sequel to existence itself. Physics tempers poetry with precision. There are equations, measurements, calibration stars, error bars, tensions between different measurements of the current expansion rate, debates at conferences, whiteboards crowded with terms that cancel or stubbornly refuse to. But beneath the human bustle is a quiet truth. The universe keeps time with its own breath. The breath is not ours to command. It is ours to observe, to describe, to understand imperfectly, then better still. Asking why is not a plea to magic but an invitation to follow cause to cause, to watch how a law turns into a pattern into a history into a meaning we can live with. And so, as you sit with this chapter, the photons on your screen or page are stretched a hair more than when they left their source. Somewhere, a galaxy we will never see is crossing the edge of our causal domain, slipping into a forever distance. Somewhere else, a star is kindling in a nursery of cold gas, oblivious to the vast fate that encloses it. In the time it took you to read this sentence, the scale factor, iten, and conda, changed by a tiny but real amount. The universe expanded, not a rumor, a fact. In the next chapter, we will go hunting for the deep levers behind this fact. We will follow the lines of evidence that convinced a skeptical community that acceleration is real. We will peer closer at dark energy, at the cosmological constant and its rivals, at the stubborn puzzle of the vacuum's faint pressure. We will ask whether the expansion has a future without end, or whether some new physics waits ahead to change the tempo once again. For now, hold this simple answer firm, if not final, in your hands. The universe is expanding because space-time, animated by its contents, evolves in a way that grows distances. Space is not the stage, it is part of the play. And this particular play, for reasons both measured and mysterious, is written to widen. Chapter 2. The Evidence and the Engines. Begin with a simple task. Hold a ruler up to the night. Of course, there is no literal ruler long enough to measure the gulf between galaxies, no tape that can stretch from here to a supercluster. Astronomy solves this with nested rulers methods that climb from the familiarity of the solar system to the dizzying immensity of the cosmos. This ladder of distance is not just a feat of measurement, it is the scaffold on which our understanding of expansion hangs. If you were making an audiobook of the universe, this is the part where the music switches to something steady and methodical, and the narrator, still slightly awed but practical, starts checking the receipts. The first rung of the cosmic distance ladder is local and precise. Radar echoes off planets, laser bounces off the moon, the clockwork of planetary orbits. Next come parallaxes, the tiny apparent shifts in a star's position as Earth circles the Sunday. Imagine holding a finger at arm's length and winking from one eye to the other. Your finger seems to jump relative to the background. That jump, translated into geometry, yields distance. The European Gaia mission has turned this old trick into a revolution, mapping the positions and motions of over 1 billion stars with exquisite precision. With nearby stars in hand, we look for patterns, stars that have a reliable link between their brightness and some other property. Cepheid variables, the pulsing giants, whose light swells and ebbs like a heartbeat, obey a tight relation between the period of their pulse and their true luminosity. By comparing how bright they appear to how bright they must be, we get distances to nearby galaxies that host cepheids. Rung by rung we climb. Standard candles leading to standard sirens, standard rulers, and standardizable fireworks. Type Ia supernovae, the thermonuclear detonations of white dwarfs, serve as candles whose intrinsic luminosities can be calibrated by their light curves. Baryon acoustic oscillations, the faint fossil of ripples in the early plasma, serve as a ruler written into the pattern of galaxies. Gravitational waves from merging neutron stars can, in principle, function as standard sirens, their chirp encoding distance independent of intervening dust. Each rung is imperfect, each has its own sources of scatter and bias, but together they triangulate reality. And when the triangulation is done, a coherent picture emerges. The farther a galaxy, the more its light has been stretched, and the fainter standard candles appear than they would in a no-acceleration universe. The implication isn't subtle. Space has stretched a lot, and recently it has been stretching faster. The words recently and faster carry a specific technical meaning in cosmology. To see how, think again of the scale factor Epris, Lu, T, our master dial. If Hismar, O Luden, A, Imini, the second derivative in time, is positive, the expansion is accelerating. The discovery announced at turn-of-the-century conferences, first with surprise, then with mounting confidence, was precisely this. Enta, Gavol by 0, A, but Don has, is greater than 0 inches the universe's late-time history, where gravity from matter alone would slow expansion like a stone tossed upward that eventually succumbs. Something with negative pressure is pushing outward gently, making the stone soar higher than it otherwise would. In Einstein's equations, pressure gravitates. Positive pressure adds to gravity's pull. Negative pressure subtracts, acting like a kind of anti-gravity on large scales. This is the core credential of dark energy. But this is a book, not a seminar, and a book must tell the human story as well. Picture the astronomers in the 1,990 seconds who gathered spectra from distant supernovae using telescopes perched above the desert air. Imagine the midnight coffee, the calibrations, the arguments about dust and bias and sample selection. They were not hunting for acceleration. Many expected to see a gradual deceleration, a universe coasting under gravity's modest brake. Instead, when they plotted the universe's expansion history, the data whispered a different story. In the past few billion years, something had tipped the scales. Meanwhile, a different cohort of cosmologists was studying the oldest light in existence, the cosmic microwave background, CMB, the afterglow of the hot early universe, its spectrum, a perfect blackbody, chilled to a few degrees above absolute zero. The CMB sky is not perfectly smooth. It is mottled with tiny temperature variations a record of sound waves that rang through the primordial plasma before atoms formed. The size and amplitude of those bumps encode the universe's composition and geometry. When all the numbers are fitted, the CMB favors a flat universe dominated today by something smooth and persistent, precisely the kind of energy that would accelerate expansion. Add a third voice: the large-scale structure of galaxies, their clustering strength as a function of scale. Galaxies are biased tracers of the underlying matter density, but with careful modeling, the spatial pattern serves as a map of the cosmic web. The BAO feature a preferred separation scale imprinted by those early universe sound waves shows up as a faint bump in the correlation function of galaxies. That bump is a built-in yardstick. Its apparent size versus redshift traces the expansion history. Once more, the favored histories include an accelerating phase driven by a component with equation of state parameter, and M's 1 W is approximately equal to -1, where amber W relates pressure and P to energy density. It must rho via all laid chorus die be cold, and 2 P equals W rock 2. Equation of state language might sound dry, but its content is potent. Ordinary matter has ready 0. W is approximately equal to 0. It has negligible pressure compared to its energy density at cosmic scales. Radiation has, and their mind, 1, 3. W equals 1 divided by 3 pressure equals 1/3 the energy density. A cosmological constant has, and 1. W equals 1 exactly. A dynamical dark energy field quintessence would have Bannier W close to, but not exactly, is N 1, 1, perhaps varying slowly over time. Observations so far herd us toward the simplest stall in the corral. Basis W very close to is a 1, 1, consistent with the cosmological constant hypothesis. Whether the very close is exactly equal remains a live question, and the effort to tighten this constraint galvanizes observatories on mountaintops and in space. Now let's ask, what could power a inbust? Is 9, 1. W is approximately equal to 1 component. The most conservative answer is the vacuum itself. In quantum field theory, every field has a lowest energy state, but lowest does not mean 0. The vacuum brims with fluctuating virtual particles, a jitter inherent to the fields that fill space. In practice, we often ignore this background energy by subtracting it out. Energies are relative, after all, but gravity couples to absolute energy. If there is a small, uniform vacuum energy, it acts like a cosmological constant. The paradox, as foreshadowed, is the mismatch between naive estimates and the observed value. If you sum the zero-point energies of quantum fields up to some high-energy cutoff, say the Planck scale, you get a vacuum energy density 120 orders of magnitude larger than what we see. Even with more sensible cutoffs, the mismatch is wild. The problem is not just quantitative, it's conceptual. Why is the vacuum so nearly empty of energy and yet not empty enough to be 0? One reaction to this problem is to hunt for a symmetry that forces the vacuum energy to cancel out, or to be exactly 0. Supersymmetry once promised partial relief, pairing fermions and bosons so that their 0-point contributions could cancel. But supersymmetry, if it exists, seems broken at accessible energies, limiting the cancellation. Another reaction is to adjust what we mean by gravity on large scales, building theories where the cosmological constant's influence is screened or where is W deviates subtly from is he 1. Scalar tensor theories, massive gravity, brain world scenarios, each writes a different footnote into Einstein's grand text. Some survive. Some falter against constraints from laboratory experiments, solar system tests, binary pulsars, gravitational lensing, or the CMB. The creativity is admirable. The universe, as always, is a stern editor. A third reaction embraces the multiverse concept. If there exist many regions of space with different vacuum energies, perhaps most are sterile deserts. In such a landscape, observers arise only where the vacuum energy is small enough to allow galaxies to form. The value we measure would then be selected by the requirement of cosmic habitability, not by a unique dynamical law. This anthropic reasoning is controversial. It risks feeling like a retreat from explanation into selection. Yet it remains logically coherent, and in some frameworks like certain string theory landscapes, a plethora of vacua is unavoidable. Whether this is the right way to think about nature is a philosophical and empirical question. Empirical here means we look for signatures of the inflationary processes that might seed such a multiverse, or for statistical predictions about the distribution of observable parameters. Before we drift too far into speculation, let's circle back to something beautifully concrete: the concordance of independent measurements. Science gains its authority not from a single silver bullet, but from a coalition of clues. The CMB fingerprints you heard about earlier aren't merely dots on a pretty sky map. They pin down the curvature of space to be astonishingly close to flat and measure the combination of parameters that shape the expansion. The supernova Hubble diagram, apparent brightness versus redshift, curves upward in a way best explained by acceleration. The BAO ruler appears at the predicted scale in galaxy surveys, gravitational lensing. The subtle distortion of galaxy shapes by intervening mass maps the matter distribution and its growth over time, aligning with the expansion narrative. Even galaxy clusters, the most massive bound structures, serve as thermometers and scales, tying the counts of clusters to cosmological parameters. Add it all up, and you arrive at a model with a handful of numbers that, while simple, describes an astonishing abundance of data. A spatially flat universe with about 5% ordinary matter, tilde 25% dark matter, and tilde 70% dark energy, expanding from a hot early phase and accelerating today. This is LCDM lambda, cosmological constant, plus cold, dark matter, the standard model of cosmology. No standard model escapes stress tests. The most publicized tension of recent years is the disagreement between different measurements of the current expansion rate. It 0, H 0 by Lemaître, and made for use knows of. Local distance ladder approaches, calibrating Cepheids, then supernovae tend to find a value of Alma 0, H 0. I have to build a mind, but I round a few km divided by S divided by MPC, higher than the value inferred from the CMB when interpreted within LCDM. Is this a subtle, systematic lurking in our candles and calibrations? Or a sign of new physics, perhaps early dark energy that tweaks the sound horizon, or interactions in the neutrino sector, or other adjustments that reconcile the early and late-time inferences? The debate is healthy. Instruments improve. Methods diversify. Tension is not a crisis. It is a chance that reality is more interesting than we assumed, or a prompt to clean our lenses. So far, we have spoken of evidence. The chapter promised engines as well mechanisms that could power expansion more directly than a constant vacuum. The queen among such mechanisms in the early universe is inflation, a brief epoch when a high-energy vacuum-like field drove exponential expansion. Inflation was not invoked to explain late-time acceleration, but to solve puzzles of the early cosmos. Why is the universe so uniform on large scales? Why is it so nearly flat? And what seeded the slight inhomogeneities that grew into galaxies? Inflation answers with panache. A tiny patch swells to encompass the observable universe, ironing wrinkles and diluting relics. Quantum fluctuations stretched by inflation become the seeds of cosmic structure. The same mechanism naturally drives an inari, a tate that grows roughly as hikrar, beether, not ht, for a brief period, an accelerated expansion par excellence. When the inflationary field, the inflaton, rolls down its potential and decays, the universe reheats, the more familiar Big Bang plasma resumes. Late-time acceleration could, in principle, be driven by a cousin of inflation, a slowly rolling scalar field whose potential energy dominates the energy density. This is the quintessence idea. Unlike a true cosmological constant, quintessence evolves in time. Its dW can differ slightly from in hey, 1, and vary. Some models have tracker behavior no matter the initial conditions. The field's evolution converges to the same path while others are more finely tuned. If observations ever detect a clear deviation of W from night 1 that also changes with redshift, a dynamical dark energy would gain an edge. Until then, the cosmological constant interpretation remains the simplest with the fewest epicycles. There is another school that asks whether the large-scale averaging of cosmic structure might subtly affect the expansion, a concept called back reaction. The universe is not perfectly homogeneous. Voids and filaments and clusters create a lumpy reality. Einstein's equations are nonlinear, so, in principle, the average of a lumpy solution is not the same as the solution of the average. Could this difference mimic accelerated expansion without invoking dark energy? Most analyses indicate that the effect is too small. The voids and walls do not conspire to generate the observed acceleration, but the exercise is instructive. It reminds us that the universe expands is a statement about averages, about the FLRW, Friedman, Lemaître, Robertson Walker, metric that describes a smoothed cosmos. Locally, bound structures do not share in the expansion. Globally, the average scale grows. Having sketched the engines and the evidence, we should look ahead. What is the long-term fate of an accelerating universe? Here the answer depends crucially on the nature of dark energy. If it is a true cosmological constant, the future is a slow drift toward a de-Sitter space-time, a universe with a fixed horizon and a steady end. Galaxies not bound to us will redshift away, their light fading beyond detectability. The cosmic microwave background will cool further, its photons stretch to absurd wavelengths. Star formation will dwindle as gas is used up or locked in remnants. Over unimaginable timescales, stellar corpses will dance and decay, black holes will evaporate by Hawking radiation, and what remains will be a dark, dilute bath of particles and curvature heat death, named for its thermodynamic flavor, not its drama. If it's too rough, W is less than infinity 1, 1. A scenario ominously named phantom energy. The expansion accelerates so violently that it could, in principle, tear apart bound structures in a big rip. Galaxies first, then solar systems, then planets, then atoms, as the scale factor races toward a singularity in finite time. This is speculative. Data do not require such a fate, and many theoretical models frown upon. Braced is safe. 1. W is less than 1 because of instabilities. If in endons, W is slightly greater than is 1. 1. Acceleration continues but with a different tempo. In some models, dark energy decays in the far future, yielding a return to matter-dominated deceleration or even recollapse if curvature conspires. Each of these futures has its own poetry and pathos, but none changes the present. The universe is expanding and, for now, accelerating. Perhaps you wonder what expansion means for the intimacy of our corner of space. Not much, at least for a very long time. The Milky Way and Andromeda are on a collision course, their mutual gravity overwhelming the expanse in between. In a few billion years, they will merge into a new galaxy, sometimes nicknamed Milkdromeda, a graceful collision choreographed by dark matter halos and stars that almost never hit. The sun will have its own rendezvous with fate, swelling into a red giant and reshaping the solar system's architecture. These are local dramas, unaffected by the breath of dark energy. On scales below superclusters, gravity stitches islands that do not drift apart, even as the surrounding sea rises. The question in the title, "Why is the universe expanding?" tempts a metaphysical coda. We could say, because the equations of general relativity, fed by the ingredients of our cosmos, demand that the scale factor grow. We could say, because the vacuum, in our best description, carries a faint pressure that accelerates spacetime's dilation. We could say, because initial conditions set by a hot birth and likely by inflation led to a universe whose natural evolution is expansion. All of these are true at their respective layers. If you press further, but why those equations? Why those initial conditions? You step onto a different floor, where physics hands the microphone to philosophy. That handoff is not a failure. It is a map of where our explanations end today. Still, the end of today's map is far from the edge of wonder. Consider the precision with which we can narrate the last 13.8 billion years, the leaps from radiation domination to matter domination to dark energy domination, the recombination of electrons and protons, the decoupling of photons, the formation of the first stars, reionizing the intergalactic medium, the emergence of galaxies along dark matter scaffolds, the quiet takeover by dark energy a few billion years ago. Consider that the photons warming your skin on a sunny day carry imprints of nuclear processes in our sun that were themselves made possible by fundamental constants that also govern how the vacuum breathes. Consider that our species, a flicker on the time scale of stars, has gleaned this much by watching carefully, arguing honestly, and building instruments that widen our senses. Let's tighten the lens once more to an equation that has guided much of this narrative, the first Friedman equation. It's 2, it's 8, A was but place, 3, but 8, love, and oh, yes, fires. 8, 2, 8, all, 2, end card, L, DS, 2, 3, H, 2, T, equals, and 3, 8 pi G, until 9s, Ron, A, 2, T, KC, 2, and friend, and H, 3, LLC, 2, he by cond, he head, by land, and 8. Here's, darned, aid is the expansion rate. He's mut, is. Rot is the total energy density of matter and radiation. Here, K encodes spatial curvature, 0 for flat, plus 1 for closed, -1 for open, and L. L is the cosmological constant. If you find equations intimidating, read it as a sentence. The square of the expansion rate equals a sum of contributions from the contents of the universe, matter and radiation, the shape of space, and the vacuum energy. Each term dilutes differently as the universe grows. Matter thins as end, in my 3, a nubble 3, volume increases. Radiation thins faster as its is all. 4, a cane, 4, volume and wavelength stretching. Curvature term scales as itri, in stand. 2, a 2, L. L stays constant. In the early, small, him, a universe, radiation, and matter dominate. In the late, large, mare, a universe, the constant term wins. The equation is a ledger, the evolution of and, well, in, is the bookkeeping. Now listen to what that ledger implies about causality and horizons. In a decelerating universe, light from ever more distant regions can eventually reach you given enough time. Your cosmic event horizon is far away or non-existent. In an accelerating universe, there is a limiting surface, a distance beyond which events today are forever out of causal reach. This isn't a wall you could fly to. It's a property of the geometry. A photon emitted now beyond that horizon can never outrun the growing space to reach you. The universe thus creates a private domain for every observer, a sphere of potential influence bounded not by matter but by the rule of expansion. This has deep implications for thermodynamics and information in cosmology. The de Sitter horizon comes with a temperature and an entropy, echoing the thermodynamics of black holes. Even in near-perfect emptiness, the universe hums with the subtlety of horizons. We should also admit the role of chance and history in how we learned all this. If humans had evolved in a much older universe where most galaxies had slipped beyond the horizon, reconstructing expansion would be far harder. If we had lived much earlier, before the heavy elements forged by generations of stars enriched the universe to make rocky planets and chemistry rich enough for life as we know it, there would be no narrators to talk. We exist in a window that is not guaranteed a time when the universe discloses itself generously. Recognizing this is not narcissism. It is gratitude. What remains unclear? Much. The precise nature of dark matter, the small-scale challenges to LCDM in galaxy cores and satellite counts, the origin of inflation and whether it even happened as textbook simple, the true value of point 0, h 0, and rado plays to all rate id fried of. He will de mud stores haze, and presumptive they old don made hod so a8. Ma geist, brado, and the resolution of its tensions, the absolute neutrino mass scale, the possibility that some future survey will find that here's W differs from OM by 1 by a hair. These are not holes in a sinking ship. They are gaps in a jigsaw that has already revealed most of its picture. That picture of an expanding universe governed by general relativity and quantum fields is robust enough to teach in schools and yet supple enough to welcome surprises. Return, finally, to the intimate posture with which we began. You, listening, perhaps walking in a park at night, earbuds in, the voice of this book winding through your thoughts. Above you, the stars in our galaxy blaze and breathe. Beyond them, in deeper darkness, other galaxies fly outward with the current of space. Their recession is not our loss. It is the shape of our story. To ask, why is the universe expanding, is to ask why there is a story at all, why the stage is not fixed but living. The best answer we have is as honest as it is grand, because geometry and energy are married, and their union writes a dynamic cosmos whose distances grow. Because the vacuum, far from being nothing, has a personality, a whisper of pressure that pushes gently, then decisively, because in its first moments the universe learned to stretch and has been stretching ever since. If this leaves you with a sense of both satisfaction and hunger, good. Science is a banquet that never empties. Every answer carries a next dish into view. The universe expands. We measure it. We model it. We marvel. And in that cycle measure, model, marvel, we find a human echo of the cosmic rhythm. Space grows, knowledge grows, wonder grows. The breath of space continues, and we, tiny and temporary, breathe with it.